Hello everybody, welcome to Fastware. Today we're going to be continuing our discussion on memory allocation, which we looked at last week, and the card is above my head right now, so have a look at that if you haven't seen it. And a quick summary of last week, we looked at implementing custom memory allocation and comparing the performance versus new. We found that we can do about 60% better than the standard new implementation if we implement a custom pool memory allocation strategy. However, the caveat that I provided last week was that the real problem is that we allocate each object individually by having vectors of objects which contain all the members, rather than having a structure where we have arrays, so structure of arrays, kind of an implementation where we can reduce memory allocation and therefore improve the performance of our application by following that approach. So before we begin, please remember to subscribe and like this video. Leave any comments or suggestions in the comment area for any future topics if you want me to cover them. So with that out of the way, please let's begin our implementation. So what we're going to do is just copy this driver code that we had from last week. We're going to rename it. So we have a stress test SoA, so structure of arrays, and we're going to copy the actual benchmark code. Before I forget, please bear with me as I'm going to be typing and talking at the same time. I'm undoubtedly going to make mistakes, but I will try to get through it as quickly as possible. So what we're going to do is we're going to remove these objects. We have composite objects and bench objects all together. And then what we're going to do is introduce a struct called bench object data, and we're going to look at what members we currently have in our bench object. So we have all of these, so we're going to put that back there, but we will make a slight adjustment. What we're going to do is we will introduce vector of each of these. Rather than having a vector of bench objects, we have a vector for each data field, I'm sorry. And we're gonna do just quickly like that. Obviously, if you're gonna be writing real high performance applications, you don't want to use vectors, but we'll get to that sometime in the future, as it is currently not particularly relevant, as I'm just introducing ideas rather than showing you how to do all of it kind of a pitch perfect. That is not the point here. We have lengths, and each of these is going to be a vector. And here we go, last one, and heights. Okay, so here is our bench object, but we also had this composite bench object. So let's have a look at that. And composite bench object has a unique pointer of bench objects in order to know which ones it wants to use. So for that, we will do something slightly different, where we're going to have a vector of std pair, and we're going to have a couple of size t's, I'm guessing. Size t. So this will now represent the beginning and the count of which will index directly into the IDs, names, widths, and lengths vectors, describing from which index we need to start to access these objects and how many of them we have. So these are our, how did we call it here? M objects. So object indices. So we will do like that. So with that done, what we'll do is follow exactly the same code as we currently have. So we will introduce our object at the beginning. So what's the name? obj, not to be crazy about it. So obj dot IDs. So what we will do is we know how many we have by saying how many buckets we need to have plus objects per bucket. So we're gonna do IDs dot reserve in order to allocate all memory up front, so we don't have to do multiple memory allocations. And we're gonna do plus object per bucket. Okay, so we have those. Now we're gonna continue with names, and we're gonna be continuing with widths. We have lengths, and we're gonna be doing the same thing for heights. So here it is. Following that, we have these this object indexes. Now for object indexes, obviously we will need only the bucket count, because this is going to be the overarching object which will tell us how to index into IDs, names, widths, and heights itself in order to access this data. So quickly we'll run through that. So obj, and so we're no longer gonna need this data. So at bucket count, and so here we have we'll need to push in. So we're gonna do pushback. We're doing place back here, and place back of. So at which object we will start, plus how many we will have. So here we obviously gonna start at 0, and we will want objects per count, objects per bucket, sorry, right here. So how we can find out which object to start? So we will do I times bucket count. So this will start at 0, then it will start at 1 times bucket count. So that will be, if we have bucket count 10. So from 10 to 20, yeah. So I think that should do the trick for us here. And then we need to populate these IDs, names, widths, lengths, and heights. So let's get to doing that. So here we have each of these members already done. So what we will do is just say, okay, object IDs dot pushback ID, and then object dot names dot pushback. The move, we want to avoid memory reallocation here, so we're gonna do that. So object dot width dot pushback, and we say width, and we're gonna say object dot lengths dot pushback length, and we're gonna say last one right here. So heights dot pushback height, right? So I think we're done with initialization, and this part of code is replaced with that. Maybe I'll just move it down in order to kind of keep it consistent as it was before. So we have all our data now here. So what we're gonna be doing is now iterating over these in order to compute this volume. So the volume computation that we had before was basically do a, where was it? Quickly. So here it is. So what we'll do is it needs to go through accumulate, and it goes through width, length, and height in order to access it. And what we're going to do is just run through all of them, multiplying these three dimensions and adding to the previous value. So what we're going to do is implement maybe a small lambda right here for us, which will help us do that. So providing that, so we have const auto cum, and we're gonna have right here, we'll provide the data. I think we can provide each vector directly, and then an index and a count in order for it to do that. So let's actually do that. So we're gonna have the constref of width, and we're gonna do constref of length, right? And we're gonna do a const ref. Right, why did I put that here? I don't know. Whatever. And then we're gonna give that pair for begin and count. So indexes. So we'll do like that, and we're gonna try to re-implement this particular behavior there. So we'll start with what was the return type here. So we had a float. Okay, so float sum, let's initialize it to 0, and we're gonna do a for indexes. So we don't need to initialize anything, so we'll do indexes. Oh no, we do, I'm sorry. So size t I equal to indexes dot first, and then I is let's do that. So L will be equal to first plus indexes dot second. So we can actually do this properly, right? So that's I is like less than L, and then we're gonna be doing I plus plus in order to do this. So now sum will be plus equals to, and then we need to do this multiplication. So we'd say widths at I times heights at I. So obviously, if you have a zip iterators, so you can put these three vectors together and actually just group them together so they would be iterated together from a specific index to the count. That would be preferable, but I don't have that implemented anywhere in my code, so I'm not going to be using that, and just a standard kind of a range loop that I'm using here, so an index loop, sorry. So, and I'm going to be returning some right here. So I think that's pretty much equivalent to what we had before. Let's double check. So we had width, length, and height multiplying, and that will do an accumulation, so a sum, and return that. So I think that is correct, what we're doing here. Right, so this is our accum, and so here we can actually iterate over object indexes. So, and here we'll have indexes. Just quickly double check. So I'm just gonna do a constref here as well, since we don't need to copy that data. That would be more preferable, I would say. Okay, and then we will replace the existing code for volume with saying accum, and here we will be providing from our object our width, object dot length, object dot heights, and then we will be providing these indexes in order to do this computation. Right, so I think it is pretty clear that we haven't done anything terribly sophisticated here. We just reduced the number of memory allocations that we have, and so we have one allocation per each of the member fields rather than for each individual object. So again, this approach is called structure of arrays, where we have a structure and it has an array of data and maybe an indexing array to tell how to access such data, which object indexes serves that purpose here for us. Okay, so what we've done here, so we can remove our custom allocation, which we had done before, and let's do a quick build. If it builds, yes it does. I think I will need to disable my quickly. I'm so sorry. Where is it? Here we go. Just need to disable our power, so it's going to be full performance now. And once we've done that, we can quickly run. And let's have a look. So each of these will have some performance characteristic at different scales. And now we have an SoA doing its thing. So we didn't reduce number of objects we had. We have exactly the same behavior. But now, for some reason, just doing the bare minimum in the simplest implementation, we already have quite a significant performance improvement. So I would say let's take this and drop into our lovely Excel file as spreadsheet, not Excel. I'm not using that, just force of habit. I'm sorry. So what we'll do is transition to our Excel. I think that's visible, should be at least. And we're going to drop this data quickly and do the usual. I want to remove this and remove this. We have more interesting data to look at. Do I need to do that? Probably not. So again, we're going to remove those two columns as they are unnecessary. We're going to keep this. I'm going to reduce that. So we're going to put these by the side. So this is SoA new, just new. And we'll be able to compare and contrast this behavior between different implementations. So using custom memory allocator or not using custom memory allocator. Okay. So obviously we'll have this printer, so we'll be able to have a look at what memory allocations we have, and we can actually then use our custom memory allocator with those specific sizes in order to see if we can improve that performance further. But let's start here. So if you remember from last video, what I like to do with these sort of measurements, I want to put them in ratio, one against the other, to see the relative improvement, because if you just graph this particular data, you tend to not get the very good results. So what I'm going to do is just going to copy this real quick now and just put ones on the kind of a baseline and do a relative performance by taking one measurement and dividing it by another. Right? This is what I have here, and I'm gonna just quickly format cells to 2DP in order to have some good data to look at. And let's do a quick line graph with a smooth step. So this is my go-to usually because I like to be able to see the data. Okay, so here it is. Our little graph now shows us that we have a relative improvement from about 1.6 to about, well, at some scales to over 2, just by changing the behavior. We got about the same when we replaced our implementation, our new implementation with our custom memory allocation. So that's pretty good. So let's see if we can make this a little bit better. So let's go back to our code. Let's transition backwards. So, and let's dive right back into our code. So close this one. So we will enable our printer in order to be able to see what is happening at each scale. And we're gonna run this one more time. 1, 2, 1, 2, 1, 2, 1, 2. Right, so we've done. So for our largest SoA test, we have one allocation of this size, one allocation of that size, and 4 allocations of this size. Right. So we have a total of 6 allocations. Let's get this into and sink in, really. Think about it. You have 6 allocations here. Now let's go back and have a look at non-SoA, which is right here. So you have 6 million almost allocations right here and over 1,000 of others. Okay, so that's quite something. So we still need to maintain this behavior right here, but then what we want to do is say, which are the largest of these? So, and I usually take the largest. So this is the largest, but we have here. Okay. So this is the largest, and I'm just gonna do a real quick calculator. Sorry, it's not going to be visible to you. But what I'm doing is taking that large number and just keep dividing by 1024 to understand what I'm actually getting here. So I need to divide twice and I get 180. So what I'm going to do is simply say that I have 200 times 124 times 124. So I'm going to take that size and add to my custom memory allocation as a specific size to be to have another pool allocator. So let's look at this allocation right here. So we have our memory allocator above, which is right here. And allocate and deallocate. And here is our memory allocation. So we have a partition of 64 bytes. So this is gonna, everything that is less than 64 will go to this memory allocator. Everything above 64, we're gonna go to this allocator, which basically is a fallback allocator with a stack allocator, size allocator, which basically just records the size. And we have a pool allocator of this size. And this is 64 aligned, and this is how many we have. And then if that doesn't fit in that size, we basically just gonna go straight to mallocator. So what I'm gonna do is I'm gonna say this is the size that we want to allocate. And we're gonna keep this to 2048 objects to be allocated. And we obviously gonna put that here. So we're just gonna, so this basically says that anything above 64 bytes will gonna be allocated. So you're gonna be allocating a large object, and we're gonna have a pre-allocated 2048 objects, and it has a 64 byte alignment. That's all it is. It's not particularly interesting. As I said, anybody can implement these pool allocators. They're fairly trivial. So we've done that. And now let's have a look at our performance. So what we're going to do is disable our printer. We're going to enable our custom. And where we are, so this is our code. Let's build this. See if we don't crash. Oh, we do crash. So let me debug that. And I'll come back in a second. Hello and welcome back after this short break where I was debugging what actually happened. It was to do with, first of all, the size of allocation that we were performing. So there was too many objects. So I changed that up a little bit. And what we currently have is I just restructured it so it would be nicer. So we have a small, medium, and large, 64, 40 kilobytes, and that's 70 megabytes or something like that, or 700 megabytes. And then you have basically the small, you have a partition between small and another partition. So anything less than 64 goes into small. Then you have a partition between medium and large. So anything less than 40 kilobytes goes to medium, and then to the rest of it goes to large. That total allocations here are counted about 1.67 gig. 1.607 gig. So yeah, and then I think that's now all working. So let's go build that, and let's do a little bit of running. So here we're running again at different states, and then now we're using our custom memory allocators for these as well. So as you can see, we have some results. So let's copy them out and paste them back into our lovely Excel, into our lovely spreadsheet. So here we don't need any of that because we know what we have. So these are the correct values. Just gonna paste them a bit further down. So here is the values that we want. So copy these. So this is well, that would be great. SoA. So, and here is our SoA data. Okay. And we can run and add, so we will start from this value, which is the standard new. And we can compute for a custom our values, which will be dividing like so. And then custom SoA, which does it take the correct? No, it does not. What we'll do is just write it ourselves. So this divided by that, and then do that. So again, we're gonna just put it nicely into formatted 2DP cells and remove this garbage right here. So this is what we saw previously. Now let's remove that and take our new data set. So again, line charts as we like them. And here it is. This is our new data set. A little too big. with this. So new is playing our baseline here, and we have standard 1. So SoA form using new is in red. As you can see, it does quite better at medium scales. At large scales, these allocations really start to cost a lot allocating such a large objects, and therefore the performance teeters off right to the end. In yellow we have our normal custom allocator using non-SoA form, so the standard kind of object-oriented objects, and that kind of sits at about 1.6 to 1.7 x performance improvement from the baseline. And in green, we have a new winner, which is using the custom allocators and a SoA form, which actually at all scales is above 2. And we can actually look at actual numbers. So in any serious processing, we have over 2 times performance improvement, up to 2.2 times, to actually solve our problem, which is actually fairly decent performance. And if we will remember that we had 1.6 performance improvement from the custom allocator and about 1.6 times improvement from actually using SoA form, so that actually kind of naively adds to 1.2, which is exactly what we sort of see. But it's anecdotal, and more measurements would need to be performed in order to actually get this right. So, looking at this data, I think I'm pretty happy now. So with not a lot of work, we actually improved the performance of our application 2.2 times, and that's fairly substantial, I would say. There's further improvements that can be made, such as all vectors can be allocated at once rather than individually, which would yield much better performance characteristics as well, since you further reduce allocation count. Also not using vectors, which hide the indirection and have additional problems for high performance code. If you're just having aligned allocated data directly, that could further improve the performance of your applications. So small things like that add up fairly quickly. So we could probably push that to probably about 3x in total if we really wanted to. But at this stage, I'm pretty happy with what we have here. So if you like this topic and you found it interesting, informative, please subscribe, like this video, or dislike it if you didn't like it at all. And then leave some comments if you have some objections, if you have some problem with my methodology, and if you have any suggestions for further topics on this channel. So with that, I will say thank you for watching, and I'll see you next time. Bye.